Okay, so when we were together last time, I did a lot of talking. You guys did a lot of listening, and so what I want to do today is to practice some of that stuff that we talked about. What did we talk about? Well, we talked about reactants. Two types: capacitive reactants and inductive reactants. I gave you a diagram, the impedance diagram, which I'll put on the board in just a second. But I mentioned the fact that you can calculate the magnitude of these quantities. Let's do this one first. So XL, capacitive reactance, XL is equal to 2 pi FL. L is the inductance and F is the frequency. Over here, XC, 1 over 2 pi FC. Again, F is the frequency, C is the capacitance. And so we'll do some calculations with that today. I also showed you the impedance diagram. Let's look at that. Let me use this purple marker. So we mentioned that we use some concepts from calculus to come up with phases for these terms over here, and that was kind of a complicated discussion, so I won't go back to that. But I will go to this. This is the complex plane. And you know, these are real numbers. These are imaginary numbers. And what I said in the last video is that resistors, and I showed the math behind it, but I won't show that, but I will just say resistors have a phase of 0. So resistors have a phase of 0, so resistors are what we call a real number. So I want to change this from the real axis to the resistance axis. And so I did that. I called this resistance. And then I did some math and I showed you that XL actually has a phase associated with it of 90 degrees. And so any number from the portion up this way actually represents inductive reactance, which means it's an imaginary number. So I'm going to get rid of this, and we're going to call this vertical axis reactance. And this part of it is XL. And then XC, we learned that it had a phase associated with it of 90 degrees. And so any number below the origin on that vertical axis is XC. So those are imaginary numbers, and we talked about that. I also mentioned the fact that you'll never measure a negative resistance. So this part of the coordinate system we don't need. We don't need that, any negative values for R. And so what I end up with is this diagram called the impedance diagram. And it looks like this. This is R, S, XL, and down here, XC. So that if I have a number on either axis, if I have a number here, I know that's resistance. If I have a number here, I know it's reactance, inductive reactance. And if I have a number here, it's capacitive reactance. Now, notice in the word reactance, you see the word react. React to what? Well, think about this. I have to make some room. If I have resistance, basically resistance is equal to V over I. It's not frequency dependent at all, for the most part. Now, that's not strictly true. I'll talk about something a little later on where you see this is kind of frequency dependent. But for the most part, you got a V, you got an I, there's no F in there, there's no frequency. So when you get resistance, it is what it is. Well, notice here, I got a frequency there, and I got a frequency there. So if I have a situation where I have a certain amount of inductive reactance, if I increase the frequency, then those ohms of opposition will go up. If I decrease the frequency, then these ohms of opposition will go down. So those ohms, inductive reactance, actually react to the frequency. Here's the opposite. Here, if I increase the frequency, this opposition goes down. If I decrease the frequency, this opposition goes up. So XL and XC are ohms whose value, the value of the is frequency dependent, so I can make it to where it depends on what my frequency is. It can vary. If I vary the frequency, I'm going to vary the ohmic value of XL and XC. So that word react and reactance, you can think of it like that. The other thing I mentioned in the last class was, well, we don't always have a number on an axis. What if I have a number out here? If I have a number out here, what that does is it represents some resistance and it represents some reactance. And so when I have those kind of ohms we call impedance. Impedance. So all these AC oppositions, I'll write them down. We have resistance. We have reactance. From an inductor, we have reactance. From a capacitor, and if I have resistance mixed with reactance, then I have impedance. I can't fit that in there. Okay, so this is resistance plus reactance. And I use the symbol Z for impedance. So if I write this down, what I could show you, I might have a circuit. I think I showed this in the last video. Say I got this. I got resistance and I got inductive reactance. So I got some R, and I got some XL, will have a positive J in front of it. I would write that like the impedance equals whatever value R is plus J, whatever value XL is. And I can express that in polar rectangular form. And this is the way we'll do it. One more thing, and then we'll do the problems. Given impedance, once I have this impedance, if I wanted to, you can, this is impedance, you can do this. I can make a right triangle out of that. And if I do that, then this side of the right triangle becomes reactance, and this side becomes resistance. So all I'm doing is I'm going to take that triangle off this diagram. So I got an impedance diagram, and the triangle I get, they refer to that as an impedance triangle. And that's usually what people work with, is the impedance triangle. And so it looks like this. And so this right angle is right here. And then this part right here is resistance. This would be reactance, my net reactance. And then this would be my impedance. And this angle right here, that angle is called theta Z. That's my impedance angle. So if I show you that way, then we can come up with the formulas you need to actually use this stuff. So my impedance Z would equal, by Pythagorean theorem, would be r squared plus x squared square rooted. And then that impedance angle there, theta z, would just be the inverse tangent. It's always the inverse tangent when you're trying to find an angle of the impedance of the reactance over the resistance. So for my impedance diagram, I can get the magnitude of the impedance, I can get the theta z, and then I can go back and forth between rectangular and polar. So we got all these terms that they're new, you're not familiar with a lot of them, but what really drives the point home is when you work problems with this. So hopefully you got a chance to print out that document. I think it was Randall. Somebody mentioned I didn't put it up on Blackboard, so I put it up there last night. I sent you an email that said, hey, this stuff is up on Blackboard for you to print it out. So hopefully you printed it out. I didn't know you guys didn't have the topic sheet. I was teaching off the topic sheet. I never put it up on Blackboard, so you didn't have it to look at while I was teaching. So I put that up there, and I put this practice problems up there, which I want you, if you had a chance to look at them, I'll go ahead and take that out. This is the one that says Circuit Analysis 2, Reactance Practice Calculations. And what I'll need from you today, you'll need a calculator, you'll need pen, paper, and we're going to just practice some of these. If you have it, some of this I can list on the board. You can just kind of work along, but you'll need to do the calculations for me. And I'm not sure that we got to do all of it. Some of these are just kind of repetitive. So we'll do some of these to make sure you get the gist of it. And if we need to do them all, we will. Okay, now number 5, I'm going to do all of those because when you have your test or quiz or however I do this with the grading, I want to have you do some of those. Those are kind of, I think, are useful. So problem number 1, they give you a list. It says determine the inductive reactance in ohms for a 2 Henry coil, and then they give you various frequencies. So you guys go ahead and work on that. Get a piece of paper, your calculator, and work on it. I'm going to write it on the board in case you don't have the paper, and then we'll do a few of these. Like I said, we don't necessarily have to do them all because once you see 1 or 2 done, then I think you'll get it. So I'll put these on the board in case you didn't get it. Let me change my black marker real quick. All right. So we have a inductor. There's 2 Henrys. And they give you these frequencies. They give you DC. They give you 25 hertz, 60 hertz, 2 kilohertz, and 100 kilohertz. And they want you to find XL for this. I didn't mention this before, but remember when you calculate XL is 2 pi times frequency times L. But if you look, that 2 pi F, you might remember what that is. Remember we had our time domain, we had V peak, sine, omega, t. We said omega was equal to 2 pi F. So basically this right here, that's omega. So you can also write XL as omega L. It's a little easier to remember. And the same with XC. XC is 1 over, I got that 2 pi F in there again, so it's 1 over omega C. So I tend to remember it this way, but just I want you to draw know that that's omega L. But anyway, let's solve these. Now, you might wonder, what do you mean frequency of DC? The frequency of DC is 0. So when you see that, that means 0 hertz. So if you apply a DC waveform to an inductor, what would its ohms of opposition be? What would it be? So let's do these problems. Again, I don't know that we got to do all. We'll do all of these, but when we get to the next one, I'm not sure we got to do all of those. I think you're just plugging numbers into a formula. Let's go ahead and do a few of these. So this right here means the frequency. DC has a frequency of 0. So basically, if I have XL, is 2 pi. If the frequency is 0, it doesn't matter that this is 2 henries. What I'm going to get is 0 ohms for that, for DC. And that's what you would expect, because XL is a AC opposition, not a DC opposition. So there's no way to measure that. Like with an ohm meter, you can't just take an ohm meter, put it across an inductor, and say XL is so many ohms. It doesn't work that way, because you got to have a frequency in order for those ohms to come alive, in order to measure those ohms. For the next one, XL is 25 hertz times pi. Let me put it in that order, the same order as this. 2 pi, my F is 25 hertz, my L is 2 henries. So anybody doing the calculations, what would this one be? I need this one and this one. Anybody got this one?
At 314.16 ohms. Is that right?
Yep. All right. So clearly what you're going to see is, as I go to a higher frequency, that number XL is going to go up. Now, the reason I wanted you to do this was because of this. What's special about this number right here, 60? Anybody know? What's special about a frequency of 60 hertz?
It's 120 volts. It's what we have in our plugs, right?
Yep. So in the United States, we have 120 volts. That is 60 hertz. That's in the USA. In Europe, I don't know if they use 120 volts, but I know their frequency over there is 50 hertz. This is Europe. And if you get on a plane like Delta, TWA, get on the airplane, it's AC on the airplane. The frequency is 400 hertz. And you might wonder, well, why is it 400 hertz on the airplane? Well, by making that frequency higher, there's certain devices that it allows them to make them smaller. Why would they want to make it smaller? Well, it's not the size, but really it's the weight. So on an airplane, by making the frequency in the airplane higher, certain devices can be made smaller and lighter. So on the airplane, this is a standard frequency for an airplane in the United States. I don't know about overseas, but 400 hertz. So I don't think we got to do all of these. I think what I wanted to point out is this one, that DC has a frequency of 0. So given that, you just put a 0 in to your calculation. This was important because this is the frequency we use in the United States. So 60 comes out a lot. If you think about it, remember omega? Omega equals 2 pi f. Well, if I go 2 pi, if I put in this frequency, 60 hertz, then what you'll get for omega is 377 radians per second. So since that's what we use in the United States, that means the angular velocity of the generator coils at Duke Energy is 377 radians per second. So when you see that this written in time domain, this number right here comes up a lot. Anytime you see like V, you might see like 170 sine 377 T. Well, that 377 is 60 hertz in there in that omega. All right, so I don't think we got to do all of those. I think you get the point. You just plugging them in. Now let me jump down to number 2. We have exactly, well, not exactly the same numbers, but now we have a 5 microfarad capacitor. We'll do a few more of those and we'll compare. So let me put that over here. Now we want to calculate XC. XC. And again, they give us DC. So DC has a frequency of 0. So XC would equal 1 over 2 pi f. But if f is 0, and then C was, I think I said 5 microfarads. Yep, this is 5 times 10 to the minus 6 farads. So what happens here, that 0, I get 1 over 0, which is infinity. So infinite ohms, basically they call this an open circuit. We consider an open to be infinite ohms. And that's exactly what happens when you have a capacitor. If you think about in DC, what happens with a capacitor is it charges up and it acts like an open. You might remember me having that conversation with you when we talked about capacitors charging and discharging. A fully charged capacitor after 5 time constants is equivalent to an open. At t equals 0 is equivalent to a short. Is how that went. So you would expect this to be what it is, so the math works out, so that's nice. And then let's do one more of these. I think the point here is to see, because of the inverse relationship between x of c and frequency, as my frequency goes up, my capacitor becomes more and more of a short. So we'll do one more of these. As I increase this, then this is going to get lower. Okay, so we'll do one more. Let's do the one with, I guess, 1800 hertz. So we'll do one more just for giggles, and then I'll move on to number 3, which I want all you guys to participate in this one. That's number 3. Number 5 is going to be something I'm going to ask on a test or quiz or whatever. I haven't gotten that figured out yet. What I did with the other class, I just got rid of all the exams. I just started giving quizzes. Because with this 10-week thing and all, I don't know how that's going to work. So we'll have to see. I like to give 4 exams, but I don't know. We'll see. But don't worry about it. That's on me. Yeah, so let's do a C. So we have a frequency of 1800 hertz. And we want to figure out XC. So let's put that into this equation. And you'll notice that it's a lot smaller than infinity. And that's the other one we did. So for this, XC is 1 over 2 pi. Now we have 1800. I'm going to leave the units off, hertz. And then C was 5 times 10 to the minus 6 farads. So let's go ahead and put that in your calculator. Let me know what that is at 1800 hertz.
Ron, you're covering up the equation.
Oh, I'm sorry. You're trying to tell me I have a big head?
I got 17.68 for that one.
All right, I think that's right. I remember that number from actually last semester. So I think that's right. Okay, so, but the point is, as this gets higher, that gets, XC gets lower, and eventually you can get high enough to XC is equivalent to a short circuit. We actually use the fact that inductive reactance goes up with frequency and capacitive reactance goes down with frequency. You can actually use that. That's several applications that I think you'll be really interested in when we get to that part. So I'll mention that later on. So what I would do, guys, is just use this to practice with. You know, just use it as a worksheet or homework. And if you do that, I think you'll just plugging in numbers to an equation, so it's really not a whole lot of solution. But if you need it, I can give you a solution sheet. I'm going to jump down to number 3. Number 3, it says express the following impedances in both polar and rectangular form. So you want to get used to doing this, polar and rectangular form. So let me put the problem on the board. And they want us to express these impedances. Now, it uses the word impedance. It didn't say resistance or reactance. It says impedance. So let me show you how you're going to write that. Impedance is Z. So for impedance, you'll have the real part, which is the resistance, plus or minus the reactive part. So for the very first one, they say R equals 6.8 ohms. So if I want to show that as an impedance, I say that Z equals 6.8. That's the resistive part, plus J0, because I don't have any reactive part. So that would be in ohms. I'll show it this way. So there it is, impedance in rectangular form, but they want it in rectangular and polar form. So if you convert this to polar form, since that J operator is 0, that means we're on the real axis. So that means my phase is 0. So this is going to be 6.8 at an angle of 0 degrees, and again, my units would be ohms. So if that J is 0, then I know, let me show you on the axis just so you see it. If the J is 0, I know I'm on this axis, so my phase would be 0 degrees. If I have a positive J, then I know my phase, that was just a positive J, my phase angle would be 90, and the negative J will be 90. If I just had the sign there, positive, negative, with the magnitude. But now, well, you'll see on the next one. So let me just go to the next one. So on B, they give you the value of the inductor, L. And again, we'll just do a few of these. I don't think we got to do them all. So they tell you L is 2 henries. And they give you omega. They say omega is 377 and radians per second will be the units. All right, so first thing you would do there is you gotta get the magnitude of XL, and that's just the equation. XL 2 pi FL, but they gave that to me. Remember, that's omega. So XL is really just omega L. They say omega is 377. Now, what you can do is just drop the radians per second. Just drop it and multiply by L. I will put the E for that. So I don't know, what is that? What's 2 times 377? 600 and I don't know what it is right now. Give me a value for 2 times 377.
574. Sorry, 754.
And my units would be ohms. So if I wrote that as an impedance, remember impedance is Z equals R plus or minus JX. So this would be, since I only have XL, it would just be 0 plus J 754. So if I wanted to show that in a rectangular form, that's how I would show it. Now, some people drop the zero. It's okay to show just the J754. It's fine. That's still rectangular form. But if you want to make it fit this, then you will put the 0 in there. So there it is in rectangular form. And what I was saying earlier, in polar form, it's real easy because I don't have a resistance. So that means I'm on the positive J-axis. That means that 754 has to be at an angle of 90 degrees. If I don't have a value here, then that J, if it's positive, means my phase is 90. If that J is negative, that means my phase is minus 90. And that will happen if I have a capacitor. So there's the impedance in both rectangular and polar form for that one. So now I think all of these are pretty much the same. So I'm going to have you guys just do these. I mean, I might make this homework. I could make this a homework, which would probably be good to do, because I don't think I'll give you a whole lot. I think I gave you one homework. So I think if you look at number 3, they're pretty much all just plugging in the formula. Now look at letter F. Look at letter F. They give you a resistance of 200 ohms and an omega of 157. So let's do that one. Now, I'm not going to say it's a trick question, but you got to think about what they're asking. We'll do that one. I have R2000. And I have omega 157.
It's 200, not 2,000. Just a heads up.
Just 200. Okay. Thank you. All right. So if I do that one, now that one's kind of I don't want to call it a trick because I hate that word. But omega has nothing to do with R. Remember, frequency resistance is not frequency dependent. So that number is just there to see if you really know what you're doing. If I want to write this in rectangular form like this, it would just be Z equals 200 plus J0. And in polar form, it's just 200. And again, if I just have that, then my phase is going to be 0 degrees. And in both cases, my units are ohms. So I think, you guys can just look at those and just do them. So I think we'll go ahead and, I don't know, I'm going to go ahead and just assign this for homework, where you guys can work all these out. You can't get on because you're just plugging them into the formula. It'll be good practice for you. But I do want to go down to, I think number 4 and number 5, I do want to do those. I want to do all of those. They're not particularly hard, but I just want to do those. I think those are important. So, well, maybe we'll do a few of those. We'll do a couple. I won't do them all, so I'm going to assign this as homework. So look at number 4. It says sketch each series circuit described below. Calculate the total impedance. Express your answer in rectangular and polar form. And then draw the impedance diagram. So that's really, really good practice. So let's do a couple of those, or maybe one of those, and then you can do the rest for homework. I'll do the first one, then you can do the rest for homework. So on the first one, they give you that the resistor value is 6.8 ohms and XL is 6.8 ohms. And they want you to find the impedance. Okay, well, the circuit's gonna look like this. I got a resistor, I got an inductor. It's 6.8 ohms. And this is, now you gotta supply the J operator. This is a plus J 6.8 ohms. So Z, here's my eyeball looking into there. The impedance I would see is Z equals 6.8 plus J 6.8, and then you would use your ohms, like that. So there it is in rectangular form. Now, to go to polar, you got to convert this over. So I got to find, basically, here's my impedance diagram. And they gave me R, they gave me 6.8 for that. They gave me 6.8 for this. So what I got to find is Z, and I got to find theta Z. So then I can use Pythagorean theorem on here. So this is going to be Z, the magnitude of Z, is going to be 6. Let me put the equation first. I mean, you should know it by now, but it's going to be R squared plus X. I'll just put X squared. This X is the net at X. So like if I had this, if I had say I had a capacitor and an inductor, if this was 8 ohms and this was 5 ohms, say I had that. Well, really, if that's 8 ohms, it's really a positive J8 ohms. You got to supply that. If this is 5, it's really a negative J5 ohms. So the net reactance here, I gotta subtract these. So my net reactance in that box, X net, is going to be 8 minus 5 is going to be 3 ohms. So that's what I mean by this is a net reactance you put in here. If I got capacitive and inductive reactance in the same line, some of it's going to go out. So if I put, and then I take the square root of it. So if I put that into the formula, I get 6.8 squared plus 6.8 squared rooted. So I need to get that number, and then to get the theta Z is always equal to the inverse tangent of the X part over the R part. So the X is going to be this. Now be careful, because I wrote this as a positive, and it is positive because my net reactance is positive. But if this had been a capacitor, then it would be a minus J right here. You have to put that minus sign down here to get the right angle. So I got 6.8 divided by 6.8. That's going to be the inverse tangent of 1. If you know anything about the tangent, if you do the inverse of 1, it's going to give you 45 degrees. So I just remember that's 45 degrees. So all I need for you to do is give me this. Give me, put that in your calculator and give me that magnitude, and then we'll write this down. What is that when you, how much?
Magnitude is 9.6.
9.6 and an angle of 45 degrees. And then you would just show your ohms like this and put a bracket around it, and we're good to go. So I think you should be able to do those with no problem. You know, just plug them in and they work type thing. Just be careful when you get to C. Well, look at B. B, they give you 2 resistors. All you do is lump them together. You add them together, and you'd have 10 ohms of resistance. But be careful at 4C. They give you 3 ohms of resistance. They give you, I don't have my glasses. I cannot see that. They give you an XL of 4 and an XC of 7. So the XL of 4 would be a positive 4. The XC of 7 will be a negative 7. So your net X will be 4 minus 7, negative 3. So you got to supply that negative sign when you have a capacitor in the circuit and they're in series. So don't make that mistake of not putting that negative sign in there. Now what I really want to get to is number 5, because at some point when I test or quiz you, I'm going to give you one like that. So I'll give you a second, read it, and then I want to talk about number 5. So it says a two-terminal AC device, and then in parentheses they call it a black box. So what is a black box? Well, black box is this. You don't know what's inside of it. You can't see what's inside of it. All you see is it's a box, and it has these terminals. That's a black box. And they're going to tell you information about the outside of the box. They want you to figure out what's in the box. So I'm going to keep reading. It says a two-terminal AC device, a black box, has the following voltage current parameters. They use the term voltage current parameters. Find and draw the simplest series circuit that will satisfy the indicated conditions. So here's what they give you. In A, they give you the voltage phasor and current phasor. Remember, we talked about this. Let me just show this real quick again. I have that Venn diagram I showed you. So these are complex numbers. And then here I have phasors. The only thing that's allowed to be a phasor is a voltage or current. And the way I'll show it as a phasor is by putting a hat on top of it. Anything else, like if I have XL or I have XC or I have Z, those are all complex numbers, but they're not phasors. So that's important. So they give me V. Now on here, on the paper, I didn't know how to make that little hat over a letter, so I just bolded it. You'll notice that V is bolded to indicate it's a phasor. So what I know about the black box is my V phasor is 120 angle 0. And my I phasor is 60 at an angle of 70. So I phasor 60 angle 70. So they gave me V, they gave me I, and what they want to know is what is a simple, based on the voltage current here that they gave you, what is the simplest series circuit that I can put in that box? What would it look like? Now, I'm gonna just let you think about that. Some of you might see it already. Don't say it. I'm gonna let you think about that. Given this, and I tell you, you have a series circuit in the box. What's the simplest series circuit you can have, given the I phasor or V phasor? How do you figure that out? So I'm gonna give you a minute just to think about it, and then I'll work it, and then you can do the rest for homework. And after we do that, what I want to do is jump right to some circuit calculations, because we've been doing this stuff for a while now. It's time to do some circuit stuff. So think about that. I'll give you a couple minutes to think about it, and then I'll show you how to do it, and then we'll move on to something new. So I'm going to sit down for a minute or two, and I'll be back in just a second to see how you did on it. See what you can figure out. All right, about 1 more minute, then we'll work the problem. Okay. So you might remember it's been a couple lectures ago, well, maybe not that long ago. I mentioned that usually when you express a voltage, AC voltage or current, you want to leave it in polar form, as a phasor in polar form. I did say, Eric, there's a few exceptions to that. We want to show it in rectangular form, and here's the exception. You actually want to show this in rectangular form because rectangular form, if you think about it, it tells you what you have. It was a series circuit. So if I express Z like this, I get R plus or minus JX. And then depending on if that J is positive or negative, I knew I would have an inductor or a capacitor in the circuit. So the first thing to do is to get this value right here, Z. So how do you get Z? Well, what you do is you ask yourself, if these were all resistors, if this was DC, what would I do? In that case, it wouldn't be Z. The total opposition would be R, but it's the same thing. You know, the total resistance is total voltage over total current. So the total impedance equals the total voltage phasor over that current phasor. That's what I would do. So I'd have to divide this 120 volts divided by 60 at an angle of 70 degrees amps. So that would give me Z in polar form. So let's go ahead and do that. So if I divide that, I get 2 and an angle of 0 minus 70 is minus 70 degrees. And since this is Z, this is now in ohms. So I just use Ohm's law on the terminal information they gave me for V and I end up with the current, not the current, but the impedance. And now what I want to do is take that impedance and convert it from polar form to rectangular form, and it'll tell me the R and X value that makes up this. So let's go ahead and convert that. So if I want R, remember R equals Z cosine of the angle, and X equals Z sine of the angle. So that's how you get R and X. So let's go ahead and do that and see what we got. R is going to be Z is 2 cosine of minus 70 degrees, and X is going to be, again, Z is 2 sine of minus 70 degrees. So let's get those values and let's see what you got. What'd you get for R?
For R, I got 684.
No, I don't think that. 684, is that right?
Oh, times 10 to the negative 3. 684 milli.
So you got 0.684.
Correct.
All right, and what about here?
I got negative 1.9. Rounded.
Okay. So the fact that this X is negative means that here's what I have in the box. I got a resistor. And the fact that that's negative, remember for the J, you got to supply the J. That's really a negative J, meaning that this has to be a capacitor. So that's the simplest series circuit you can have. The value would be 0.684 ohms for that. And then for this, minus J 1.9 ohms for that. So that's how you tell what's in the box, the black box. So I think that will do it for that sheet. I want you guys to work all of these problems, and I actually might count this as a quiz. I'm not sure if I got a quiz grade up for you guys. I need to do that. This should be easy enough. If I do it as a quiz, it'll probably be a guaranteed 100 because you should see how to do it. So go ahead and work on this, and I'll either have you submit this as a homework or a quiz. I'll think about it. And then you'll be able to upload to Blackboard, and I'll let you know. I'll send out a link here in the next day or so. But go ahead and work all the even the ones we did in class. Just work it all, and you'll send it to me, and it'll be kind of pass-fail, whatever it is. Either you got it or you didn't. You're just plugging numbers in the formula, so it's not a whole lot of thinking here. So does anybody have any questions on this sheet? I want to assign it. I might assign this as a quiz. So if I do, are you clear on how to do it with the examples that we went over today? Anybody have any questions?
I would be okay, but just real quick on a light side note, I know that we've been recording sessions, but I can't seem to find the actual lecture recordings themselves on Blackboard.
Yeah, so what you have to do is if you click on the collaborate link on your Blackboard, and when you do, as soon as you click on that, you click on the collaborate link, and in the upper left-hand corner, it looks like this. It's an icon. Right over here is an icon. It looks like that. You click on that, and it'll say recordings, and then you'll be able to see all the recordings that we've done.
Okay.
And if you have any trouble, let me know. I can show you. I tried to upload. I had one long video that we did, like the one we did last time, was ridiculous. That was a long lecture, and it's just too hard for me to upload on the YouTube. I like YouTube because you guys have access to it. You can open it up on any device, and it's just better. But I tried the first day to put it up on YouTube, and my computer just kept spinning, so I just said I'd leave them on Blackboard. But they do kind of have it hidden. It's hard to find because you're like the third person to ask me where they were. So they ought to have some kind of thing there to show you where they are.
Okay.
So, all right. Well, if you don't have any questions, I want to move on to actual circuit calculations. How would you use this stuff to solve series circuits, parallel circuits, combination circuits? What would you do with power? All that stuff we did last semester. How we're going to do it in AC. So I want to start by giving you a problem. And I don't know if I have this on Blackboard or not, but it's just an example. I probably should put it up there because the order I have this in is the order that you'll do all your series calculations. But you work along with me and just kind of help me calculate, and I'll show you how to do a series problem. And then what I'll do is I'll put some other problems up on Blackboard where you can show me that I can really just follow what I did, but this shows you the steps in nice, simple chunks. So let me put it on the board because I don't think I have it up on Blackboard yet. And you can copy it down and we'll go through it. But it's important to remember that the way I have these numbers, 1 through 5, it tells you kind of how to solve the circuit. I'll read it out loud. You'll see what I'm saying. So let me put the circuit on the board first, and then we'll do the calculations. So I have a series circuit, a series AC circuit. And here's all right, so I got R, I got L, and I got C. They tell me this is 100 ohms. They tell me this is 0.265 henries. This is 53 microfarads. So there's my circuit. And then I don't have enough room to write my voltage. So they give me this in time domain, and they say that that voltage, I'll put that in a different color so you can see it. That voltage is 141.44 sine 377t. So here is my voltage. This V is that. And I'll read this. So you want to write these steps down as we go through the problem. And what will make it easy if I give you like something like this as a quiz. If you write down like number 1 and then an example of how to do it, then when I give you this, you can just follow this and copy it over to the quiz. So the very first thing it says under, it says convert all power convert all power sources to phasor form. Right now, they gave us this in time domain, the one in the phasor domain. So your first task is to convert this to a phasor. So you go ahead and do that, and then we'll do it together. Write it on the board so you'll have the list of, because all of them are done the same way. So the first thing A on there says convert sources, either voltage sources or current sources, to phasor domain. Okay, so convert that to a phasor. So if I convert that to a phasor, now instead of writing V like that, I'll write a capital V with a hat on it showing it's a phasor. What would you get for the magnitude of that phasor? What would you get? Or if you don't know what you would get, how do you convert from time domain to phasor domain? What do you do? And we did like what, 3 or 4 of these. How do you convert it to a phasor? So to convert it to a phasor, I got to take this is my peak value. Go ahead. What'd you get? Somebody has a baby in the back. So 707. And if you do that, what do you get for magnitude?
99.99.
So basically 100.
Yeah.
at an angle of, since there's no phase angle here, 0 degrees. So 0 degrees and my units are volts. So if you forgot how to do this, to go from time domain to phasor domain, just take the peak value, multiply by 0.707, it gives you the magnitude in RMS, and then the phase angle is whatever is written here. You write that right here. If there's nothing there, that means that phase angle is 0. So what that means is I can get rid of this and show this as 100 angle 0 degrees. My units are volts. So I can get rid of this. You never want to work in time domain. You always convert it to a phasor. All right. So we've done that part. Now, the next part says, number 2. Well, I'm showing the A. It should have been a 1. It's 1, not 1, number 2. Find the ohmic value for all capacitors and inductors in the circuit. Show each opposition, including resistance, in both rectangular and polar form as defined by their respective positions on the impedance diagram. So in other words, right now, none of these are in ohms. The only thing that's in ohms is a resistor. So I have to convert the L to XL, which is ohms, and the C to XC, which is ohms, and then I want to show them both in rectangular and polar form. And I'll do that for all my oppositions. So let's go ahead and do that. So the second part is to convert all oppositions to polar and rectangular form. All right, so that's already an opposition. So to convert this to opposition, I got to change L to XL by doing this. It must have gave me the frequency here. Let me see. Because I didn't write. Oh, you know what it is? I don't need that. Remember, in my original formula, they gave me V was a 141.44. They gave me sine 377t. So they gave me omega. So remember, this right here is really omega. So I can really write this as omega L to convert it over. So I'm going to use that 377. I thought they gave me frequency. You need either frequency or omega to do that. Without it, you can't convert it. So they gave me omega 377. So this is going to be omega L and 377, and L is that'll convert this to XL, and I want to convert that to XC by doing this one. 1 over omega C. It's going to be 1 over 377, 53.03 times 10 minus 6 farads. Okay, so if you calculate,
Is it 5303 or 5305?
You're right. Oh yeah, I wrote it over here. All right, 5305. Thank you. All right. So give me XL. Tell me what that is. How many ohms?
That is 99.9, so 100 ohms.
100 ohms. So right away, get rid of this. You don't ever want to work with L or C in the AC circuit unless you're doing something making filters, which we'll talk about towards the end of the semester. So this right here is in polar and rectangular form. So in polar form, it's just plus J 100 ohms. And then, rectangular, this is rectangular. In polar form, it's 100 at angle 90 degrees. And this is in ohms. So it tells you to show this opposition. I can change that now to XL in rectangular form and in polar form. And the reason is as we do our math, as we continue, sometimes, remember, if you add or subtract, you want to be in rectangular form. Well, there it is, conveniently there for you. When you multiply or divide, you want to be in polar form. You got it right there. You don't have to think about it. So that's why they want you to show it in both polar and rectangular form. Okay, so that's XL. Now let's get XC. Give me the value for XC.
$50 ohm.
How much?
$50 ohm.
50.
Yes.
All right, so when I write that, I'm going to get rid of this. And you guys, that's really, if it's 50 is a minus J50, you got to put that in there. This math will not tell you that. So I'm going to put this in rectangular. It's a minus J50. And in polar form, it's a 50 and an angle of, if my J operator is negative, this has to be a minus 90. All right, so there it is. Here's my rectangular form of resistance. My polar form of resistance would be 100 and an angle of 0. I wanted to show both forms. So there are all my oppositions converted over to ohms and expressed in both polar and rectangular form. Let's see what the next thing is we got to do. We got all our oppositions. Now, number 3, it says for a series circuit, find the impedance, the total opposition, by adding all the resistances and reactances in rectangular form and then converting the result to polar form. In other words, you don't even have to follow the list there. Now this is like a DC problem. Because I'm using phasors, I can treat this as if it were DC. And if this was a DC series circuit problem, how would you solve it? They're all done the same way. The first thing you would do is find your total resistance. If this were DC, in DC, well, here we're going to find our total, not resistance, we'll find our total reactance. So how do I find my total reactance? Well, in the series circuit, all my oppositions are added up. So ZT, my total reactance, is going to be this plus that plus this. That's a negative number, so I wrote it as a negative. So let's put our numbers in there and see what we get. I have R of 100. So now notice I'm adding now, so I'm using all my rectangular forms that I have written here. So R is 100 plus A, XL is 100, XC is minus 50. So then I end up with ZT equals 100 plus J50. And my units would be ohms. So there's my total impedance. And now what you want to do is take it from rectangular and convert it to polar. We always want to work in polar form. So I got to convert this over to polar. And that's how I express my answer for Z. So I want to convert that to polar. I got to find the length of my radius vector. So the way you do that, I'll just say the magnitude of Z is going to be R squared plus X squared. That's this X net. That's this value right here, square rooted. And then my theta Z is going to be the inverse tangent of X over R. So by now you should probably know this formula. We've done it, talked about it so many times. So I got 100 squared plus 50 squared square rooted And then down here, I got the inverse tangent of 1/2, 50 over 100. So give me my value for Z. I guess I'm calling it ZT. So give me this value.
It is 111.8 at 63.4 degrees.
You said 111. 111.8 angle what?
63.4.
And that would be in ohms. So that's the way you want to show it. It's about 112. So there's my total opposition. In a DC circuit, it would be my total resistance. So what would be the next step? Well, once I get my total resistance, I can find my total current using Ohm's law. It's exactly the same thing here. You just follow what you would do if this were a DC circuit. And the reason, again, we can do that is because we're using phasors, and phasors kind of equate AC and DC together in terms of heating effects. So we can treat an AC circuit as if it were DC. So I'm going to find my current phasor. My current phasor is equal to my voltage over my opposition, but it's not resistance, it's impedance. Now notice I don't have a hat on the impedance because it's a complex number, but it's not a phasor. The only phasors I have is here. I'm taking my voltage phasor, divided by this other complex number. The thing I got is still a phasor. So I have 100 angle 0 divided by 111.8 angle 63.4 degrees. By the way, when we got this number, we should have been checking the quadrants. Remember, we were in quadrant 1. This is the reason this worked out. But if we had been in quadrant 2 or quadrant 3, we would have to add 180 to the angle we got. So don't forget about that. I haven't done any problems like that, so it's easy to forget about. But we did some practice to help you to think about these phasors and these complex numbers where they are. So somebody take 100 divided by 112, and let me know what that is for current. And then I'm actually going to draw the current like we do in DC. So what do you get with that?
I got 0.892,
Okay.
and then at negative 63.4 degrees.
So you said 0.852,
892.
and the angle would be minus 60. That's about right. Let's compare those. Okay, so I'm going to use a certain color. Remember your color coding. I don't know if this red shows up or not, but I'll go ahead and use red for my current, and I'll just show that. If you want to show it in milliamps, you could. You can move it over and show it in milliamps. I guess that might be a little better. I might show it in milliamps. So 892 angle. I'm gonna have to get rid of my angle minus 63.4 degrees, and that would be in milliamps. I don't know if I should have showed it in milliamps because none of these are in K. So I probably should have left it in amps, but it doesn't matter. You can see what I'm doing. So I got my current. So now what do? Well, if this were DC, to completely solve the circuit, we got to find voltage drops. So how do I find the voltage drops? Well, once you get the current, it's just I times R. If this was DC, well, in AC is I times whatever the opposition is. So we got to find all of the voltage drops. So let's do that. So the first voltage drop is a voltage drop across this resistor, which I erased, but it was 100 ohms. So VR is equal to I times R, and that's a phasor, and that's a phasor. So you put a hat on those. Well, I know that this is a 0.892 angle minus 63.4. I'm going to run out of space. So I'm going to have to not write the equation. So a VR hat is a current which is 0.892 angle minus 63.4. And that is now in amps times 100 and an angle of 0 degrees. So it's I times R. And that'll give me 89.2 at an angle of minus 63.4. Now we're in volts. Now I want you to notice something. Look at the phase on my resistor voltage and look at the phase of the current. What do you notice? They're the same. And remember what we said? We talked in the last class about this. In a purely resistive circuit, the voltage and the current are in phase. So anytime I have a resistor, the voltage through the resistor is in phase with the current through the resistor. I should say the voltage across the resistor is in phase with current through the resistor. If I have just XL, then I gotta use that Eli the Iceman. Eli Iceman. So if I have an inductor, then voltage comes before the current. If I just have the inductor by itself, the phase is 90. If I have a capacitor, then the current's going to come before the voltage. Again, the phase would be 90, but that's not what we're doing now. Let's find the voltage across the inductor. So let me put a box around this so it's easy to see. And now what I want to do, I'm going to have to erase some of this stuff. I want to find the across the inductor. We're going to call that VL. So VL is going to be the current times XL. So the current times XL, 0.892 angle 63.4 amps. I have a series circuit, so the current is the same everywhere. I'm going to multiply that by 100. Angle 0. No. Angle, not 0. 90. This is ohms. So if I multiply that, again, I'll get 89.2. And that'll be what? What is it? 40, 37, 30, is it 36, angle 36.6 or something? Is that right? I can't really do this in my head when I'm tired and like I am now. Check me on my arithmetic here. Is that 36.6?
26.6.
26.6? You said 26?
So I'm coming up with.
Okay. Seems like it would be okay. That'd be 40. Oh, okay. I'm thinking 100. You're right. It's 90. I'm thinking that's 100. Forget it. All right. So we got that. I'm going to put a box around there, and you'll see why in just a second. And the last one is the voltage across the capacitor. I never got rid of that C. That's really an XC now. Let's get rid of that. This is XC. All right, so let's do the last one. We have VC now. Hopefully you can see it if I write it this low. VC, actually I can put it right here. Put it right there. So VC is I times XC. I'm using this one because I'm multiplying. So it's 50 angle minus 90. I guess, okay. So that's going to be, I don't know. It's half of this number down here. I know that. So what do you get when you do the math here?
I have 44.6 and degree
44.6 and the angle what?
angle is negative 153.4.
All right. So now we got all of our, and this should have a hat on it. This one is a phasor, and that's a phasor. So now we got all of our voltages. Let me put a red box around it so you can see it. Because the last thing they want us to do to finish the problem out it says on the sheet, it says verify KVL. What does that mean? Verify Kirchhoff's voltage law. So let's verify it. Well, my total voltage is 100. So all of these voltage drops got to add up to 100. So I got a problem already, don't I? Because that's 44. That's 100. So I'm at 144, 145. That's another, no, it's 44. I'm not looking at that. So it's 44, 89, and 89. Well, already I'm over 100. So what's the problem with this? Did we make a mistake? How come they're not adding up?
Is it because the conductor is inverse to the resistor?
Okay, good guess. When we add complex numbers, what form do we need to be in? You can't add them up in polar form. It won't work. Well, you could. If you had a ruler and a protractor to get these angles, you could actually do it graphically. But in order for this to happen, now I'm not going to do it on the board because I just don't have enough space. Normally on campus, I do it on campus, but there's no way I can do it here. But what you'd have to do is convert all of these, everything in the red box, to rectangular form. And then convert this to rectangular form. Well, that's easy. If I convert that to rectangular form, this voltage right here, that's the total, would just be 100 plus J 0 volts. Right? So what you would do is convert that to rectangular, convert that to rectangular, convert that to rectangular, and then add them all up, and it better add up to this. That's what they mean by verify KVL. So I'm going to leave that for you to do as an exercise to see. We've done all the work. All you got to do is convert each of these in the red box to rectangular form and see if it does or does not add up to this. And I'll ask you about that in the next class. See if it checks out. And I think you'll find that it does check out. So this stuff is like really labor intensive. Look how long all the stuff going back and forth between forms. You got to do all of this stuff to do a simple AC problem. And that's what makes this course a little bit heavier than just DC. And we haven't even done anything yet. We're just getting started here. Now, I will say that I don't know what kind of calculator that you have. If you have a scientific calculator, most of them will do the conversion from rectangle to polar and vice versa. You can do that automatically on your calculator. You don't have to do the square root thing. It's good to do it by hand until you see what's going on. But once you see how to do it, I would just put in the calculator and automate it. So if it's a T calculator, you can just go on YouTube, put in your calculator model, and ask it how to convert, and it'll walk you through it. If it's another kind, you have to look in your owner's manual and figure it out. But most calculators, probably all scientific calculators, will go from polar to rectangular and vice versa. Because that polar stuff, that's not an AC thing, that's a complex number thing. Okay, so I think that's it, guys. I had the schedule to go to 4:20, but I think from 2 to 2:30 is enough for me. Only thing I want to tell you is go ahead and make sure she had the one that I said I want to count as a homework or a quiz. Don't wait until you hear from me. Go ahead and do the problem. So no matter how I tell you to submit it, you'll have it done. And then I would recommend going back through here and actually converting these over and checking to make sure that you can apply KVL. Now I have 2 more assignments that's exactly like this. So you'll pretty much just have these notes, and you can just kind of follow the steps. Because what I want to get you used to is just kind of thinking like this. And it's exactly the same thought process as in DC. It's just that you gotta worry about these angles and all of that stuff, keeping that straight. So other than that, it's just like DC. Any questions for me before we sign off? Because this is going to be it for today, I think. Any questions or comments? Concerns?
I just want to point out that I did email you Lab 1 before uploading it through Blackboard, so you might see an email from me.
Do you have it? Do you still have the lab? Is that Sam?
Yeah, it's me, Sam.
Do you still have the lab?
Yeah.
Go ahead. Are you able to scan it?
Yeah, I got it scanned, but I sent you the link via email. But I've now sent it through Blackboard as well. So just ignore the email from me.
Okay. All right. I see what you're saying. Okay, I remember. Okay. Guys, have a great rest of the day. I will see you. What today is Wednesday, so I won't see you for a few days. So have a good weekend. I know it's going to warm up out there a little bit. And I'll see you Monday. What we'll do some more of this stuff. I want to show you a parallel circuit, and then it gets kind of tough when we do. It doesn't really get tough. We do series parallel. We're going to kind of keep things pretty simple this semester, given the amount of time that we have. We can't. There's no way to get into this in the kind of the details like we would if we had a full 15 weeks. I know the times are the same, but I think 2 4.5-hour sessions are the same. So have a great rest of the day. If you have any trouble finding those links of the recorded videos, let me know. I'll call you on the phone and walk you through it. And other than that, if there's anything that comes up, send me a text, and I will talk to you guys later. Thank you. Jacob, are you here?
Yeah, what's up?
I don't want you. I just want to know why you haven't said anything for the whole session. You just
Do
quiet.
do I have to speak?
Yeah, you're supposed to give me at least one. I think that was your daughter in the background.
Nah, that's somebody else's. Mine isn't that young.
Oh, you muted it? Okay.
Yeah,
Well, I was
nah,
wondering 'cause I usually...
my kid's speaking sentences now.
Okay. Well, somebody got some catching up to do, I guess, with your kid.
Yeah,
Okay, I was just checking.
somebody's got a fresh one somewhere.
That was
Okay.
the floor threshold.
That was your daughter? Okay. All right. Well, guys, take care, stay safe, and I'll talk to you on Monday.
I
Thank you. Bye-bye.
Bye.